One important microwave devices used in microwave communication system is the detector. A detector converts radio frequency to DC. It can also demodulate AM and pulse modulated radio frequency signal. Detectors are used in power meter to measure microwave power in terms of average power, pulse power, and also peak power. The operating principle of a microwave detector is that the output current is proportional to the RF power. In other words, the output current is proportional to the square of the voltage, RF voltage. Therefore, this detector is also called a square law device. Some example of detectors used in microwave communication systems are the point contact Schottky diode and Esaki tunnel diodes. This is a typical diode detector circuit. The diode is a rectifier with a radio frequency signal at the input. The diode is turned on for half a cycle and turned off for the other cycle. Therefore, at the output of the detector, we get a half-wave waveform, and with a bypass capacitor which acts as a low-pass filter, the half-wave waveform is converted to a DC, which we call a video output, because the RF signal at the input may be pulse modulated or AM modulated. So in that case, we have radio frequency with a certain envelope instead of a continuous wave. Therefore, the output will not be DC voltage, but voltage that follow the envelope of the AM waveform. Of course, the input impedance of the diode detector may not be match impedance. So typically, we will need a input matching network. Another device that is commonly used in microwave communication system is the mixer. When we select a mixer to be used in our design of microwave transmitter or receiver, some of the important parameters that we need to consider include whether we should select a single balance mixer or double balance mixer, depending on the performance requirement. Of course, a double balance mixer will give a better performance at a higher price. If we want better performance, we can also select the image reject mixer, and in some application we use IQ mixer. Typically, mixer are made of diode. That means we have a passive device, and there is no gain but loss in the mixing process. If we need some gain at the output, we can make use of active mixer such as Gilbert cell mixer. Some of the important parameters or specifications to consider include the VSWR at all three ports, the RF port, the LO port, and the IF port. Next, we need to consider the LO power required for the mixer to operate. The LO power must not be too high or too low, depending on the specification of the mixer. If the mixer is a passive mixer, we'll get some conversion loss, and if we use an active mixer, we'll get some conversion gain. However, the gain may not be linear, like in the case of amplifier, there will be a 1 dB compression point, beyond which we will get much more distortion or harmonics. And similarly, a mixer may also have IP3 specification and noise figure specification. Another important parameter to consider is the isolation between the RF port and the IF port, between LO and IF, and between LO and RF port. When a mixer is operated beyond the 1 dB compression point, or if the mixer does not have a good performance, such as the case of a single balance mixer, we may get some spurious output, which is basically intermodulation between the various input to the mixer. The spurious output frequency can be given by M times FLO plus or minus N times FRF, where M and N are integer. Another device that is used in microwave system is the microwave switch. Microwave switch can be constructed using circulator with the permanent magnet replaced by an electromagnet. Remember that the operation of a circulator is that it will circulate the input signal at port 1 to port 2 and not to port 3. That is because of the direction of the permanent magnet. So if the polarity of the magnet is reversed, the input signal at port 1 will be circulated to port 3 instead of port 2. That way, the signal can be switched between port 2 and port 3 by controlling the direction of the permanent magnetic field. We can also make microwave switch using mechanical system. There are different types of mechanical switches. Some has a single pole, single throw, a single pole, double throw, or single pole, multi-throw. The shortcoming of mechanical switch is the switching speed. It may take several milliseconds to hundreds of milliseconds to change the switch position. If we need a faster switching, we will need to use semiconductor switch made using a pin diode or field effect transistor. In the selection of microwave switch, some of the important parameters that we need to consider include the bandwidth, the switching speed, off-state isolation, and power handling capability. When the switch is off, the output is cut off from the input. However, with this open circuit, the switch presents some capacitance to the transmission line. So one parameter to consider is the off-state capacitance, which will affect the bandwidth. And another important parameters is the on-state resistance. That is, when the switch is turned on, the resistance between the input and output port. This is an example of a microwave switch. There is one input and two output. The switch position is controlled by voltage applied to this terminal. This is an example of a semiconductor switch, which is in the form of a chip. There are different design of semiconductor switches. We can design a single pole double throw switch in a series configuration or a shunt configuration. In a series configuration, the signal at port 1 is connected to port 2 when this transistor is turned on and the second transistor is turned off. Similarly, if we wish to switch the input signal to port 3, we can turn off the second transistor and turn off the first transistor. However, the transistor may not be totally turned off, so typically there may be some leakage from port 1 to port 2 when the transistor is off. We can improve the performance using a shunt configuration. In this case, we make use of quarter wave transformer. If signal at port 1 is to be transmitted to port 2, transistor number 1 is turned off so that it is equivalent to an open circuit, whereas the second transistor is turned on so that it is equivalent to a short circuit or a very low resistance. With the quarter wave transformer, which acts as an impedance inverter, a 0 ohm or very small resistance is transformed to a very high impedance, close to infinity. Therefore, the input signal will be isolated from port 3, and all the signal will be transmitted to port 2. This will reduce the leakage from port 1 to port 3. And further, with the transistor turned on, port 3 is shorted to ground, and this provides additional isolation between port 1 and port 3 when the second transistor is turned on. To improve further the isolation, we can use a combination of series shunt transistor. In this case, when the signal is to be transmitted from port 1 to port 2, the first transistor is turned off so that we have open circuit. In other words, port 2 is not short-circuited to ground. And the second transistor is turned on so that port 1 is connected to port 2. The third transistor is turned off to provide isolation between port 1 and port 3. To improve further the isolation, the fourth transistor is turned on to short port 3 to ground. We can also use a shunt series configuration. The operation is similar to the earlier case, but this time additional transistors are used, and quarter wave transformers are also added. So when the first transistor is turned off and the second transistor is turned on, signal is connected from port 1 to port 2 through the quarter wave transformer, and this transistor is turned off so that port 2 is not shorted to ground. But for port 3, we need a good isolation. Therefore, this transistor is turned off, and the fourth transistor here is turned on to give us a short circuit. And furthermore, this transistor is also turned on to short port 3 to ground. That gives us a better isolation. And further, the quarter wave transformer will transform the short circuit to open circuit, and that provides additional isolation between this point and this point. Some applications of microwave switches include the TR module, stands for transmit receive module. It looks like this. It facilitates a half duplex operation. A transistor can, an antenna can be used to transmit and also to receive signal. When a signal is to be transmitted, the switch is connected to the transmitter. When the transceiver is to receive a signal from the air, the switch is connected to the receiver. The transmit signal and the receive signal can be of the same frequency because this is time division multiplexing. A microwave switch with 1 to n channel or single pole multi-throw switch can be used to perform time multiplexing. A signal at the input can be switched to various outputs depending on the requirement at different time. We can also use a switch to modulate radio frequency signal such as the ASK. When the switch is turned on, an RF signal is transmitted, and when the switch is turned off, no signal will be transmitted. A switch can be combined with transmission line with different length to make a phase shifter, a variable phase shifter. As we know, different length of transmission line will give rise to different delay or different phase shift. So by utilizing two switches, we can select the transmission line to be used and therefore obtain the different phase shift. We can also make use of diodes to make switch and combine with transmission line to make phase shifter. This is an example of a 2-bit phase shifter. The diodes are turned on or off by the bias voltage at this point and this point. So when the voltage is positive, this diode and this diode is turned on, and whereas these two diodes are turned off. This quarter wave transformer allows DC current to flow from the positive voltage through the two diodes to ground in order to turn on the two diodes. However, RF signals is not shorted to ground because the length of this transmission line is a quarter wave length. That means a short circuit is transformed to an open circuit. So this point is isolated from ground by the quarter wave transformer. So if we wish to select another transmission line, we can switch the bias voltage to negative. This time the first two diodes will be turned off because they are reverse bias, but the other two diodes are turned on. And the same goes for the second bit. We can control the diodes to be turned on or off using a bias voltage at this point. So if this transmission line and this transmission line are selected, um, we have the lowest phase shift. But if this transmission line is selected, then we will get an additional 20-degree phase shift, and if this transmission line is also selected, we will get an additional 40-degree phase shift. That means using these two voltages, we can get 4 different degree of phase shift. Attenuators can be made using various circuits. This is a T attenuator consisting of a T network, and this is a pi network attenuator. We can add an additional resistor to the T attenuator to make a bridge T attenuator like this. So the value of R1 and R2 will determine the amount of attenuation. However, in the design of an attenuator, not only we want to get some attenuation, we also want to have impedance match at both the input and the output. So it is not simply selecting or changing the resistance R1 and R2. We must select the value R1 and R2 properly so that we achieve two targets at the same time. That is getting the attenuation and impedance match at the same time. So with a bridge T attenuator, these two resistors are selected to have to be equal to the characteristic impedance of the input and output, and the value of R1 and R2 are selected to achieve the required attenuation and impedance match. We can also make attenuator using combination of hybrid coupler and resistor. Notice that in this design, we have only one resistance, that is R1, compared to the earlier case where we have both R1 and R2, which must be change at the same time if we wish to make a variable attenuator. In the reflection type attenuator, we only change one resistance to get the different amount of attenuation. This is the symbol for a hybrid coupler. It can be a 90-degree hybrid coupler or 180-degree hybrid coupler. When the signal is connected to the input, half of the signal is transmitted to port 2 and half of the signal is transmitted to port 3. The signal transmitted to port 3 is terminated by R1, which may not be match impedance. That means we will get some reflection The reflected signal is again split. Half of the power will go back to the input, and half of the power will be transmitted to port 4, which is again terminated by R1, and this will also give rise to some reflection. The reflected signal is again split into two. Half of it will be shorted to ground by R1, and the other half will be added to the signal that is transmitted directly from the input to the output earlier. The output power here is not exactly half power. When a signal is connected to the input, half of the power is transmitted to port 2, but because of the reflection from this resistor, and this reflected signal may be in phase or out of phase compared to the direct transmission from port 1 to port 2. So whether the reflected signal is in phase or out of phase depend on the value of R1, whether it is larger than the characteristic impedance or smaller than the characteristic impedance. So when the reflected signal from from port 4 to port 2, if they add in phase, we get slightly larger power, and similarly, if they add in opposite phase, we will get less than half power. And that means by varying the value of R1 to be larger or smaller than the characteristic impedance, we can get the different value of attenuation. However, one shortcoming of this reflection attenuator is there are some signal that is reflected by this resistor back to the input. In other words, we do not get impedance match at the input. To improve the impedance match at both the input and output, we need a balanced design. This is how it looks like. We make use of two hybrid coupler. So when the signal is connected to the input, half of the signal is transmitted to port 2, half of the signal is transmitted to port 3. And similarly, by controlling the value of R1, some of the signal will be reflected by at port 2, some of the signal will be reflected at port 3, and both reflected signal will be split between port 1 and port 4, and because this is a hybrid coupler, the reflected signal from port 2 back to port 1 and the reflected signal from port 3 back to port 1 will always cancel each other. Therefore, no signals are reflected back to port 1, and this is how we get the impedance match at port 1. Similarly, different value of R1 will give rise to different amount of reflection, and therefore different amount of insertion loss. or attenuation. And the signal that is transmitted will add up at the output. So if there are more reflections due to mismatch of R1, we will get the higher attenuation or lower power at the output. For the pi network and T network, remember we want to achieve two objectives at the same time. We're going to get a certain amount of attenuation K, which is the ratio of output voltage to input voltage, and we want the impedance to be matched at the input and output. This can be done by selecting the value of R1, R2 and R3 according to this formula for pi network and according to this formula for T network. This is the example of the pi network implementation using microstrip line. The input resistance is given by these two resistors connected to ground in parallel, and the output resistance is given by these two resistors connected to ground in parallel. Using two resistors instead of one reduces the parasitic inductance, and this will improve the performance of the attenuator.